So welcome everyone to this round 2 of the MMS Quickfire talks. I'm gonna have to start with a bit of an unfortunate announcement. We usually do 3 of these Quickfire talks, but Lyndon, who was like a guest speaker, who was supposed to give a talk on financial mathematics, unfortunately he's unwell, so he wasn't able to come today. So we're gonna have 2 talks. Okay, so we're going to have Adriana first. Is going to talk about how maths ties in, or something related to maths and computer science. And then Ethan will give a talk about like the same thing, but for physics. So like physics and maths. Okay, so Fidek, Adriana.
So hello, welcome to the talk. I chose this topic because it's something that we all use day to day. When we go on the internet to send any information, we have to encrypt and decrypt our information. So a couple of motivating questions. So how can 2 people share a secret in a crowded room? How can 2 people flip a coin over the telephone when they don't trust the other person? And how can you send your credit card details over the internet when someone can just easily listen in? So obviously I won't answer these directly, but this talk would hopefully give you the tools to answer these questions yourself. But to get to this, we need to take a journey into a whole different topic, which is modular arithmetic, which is called sometimes clock arithmetic. So why is it clock arithmetic? So what is 1300? You know, fairly easy question, but what you're doing is you're going around the clock, you're wrapping around a string of length 13 and you're seeing where it goes. So you get 1, right? So what is 2100? You do the same thing, go around 20 times around the clock and you get to 9. And that's the whole concept of modular arithmetic. It's what remainder do you get when you divide by 12, for example, right? So the concept is, it's done in primary basically. We learned that 15 division by 8 gives us 1 remainder 7. In modular arithmetic, we throw away the 1 and we keep the 7. So we say that 2 numbers are congruent mod n if they have the same remainder. So in this system, 4 is equal to 8 mod 2 because they both have remainder 0. We need to delve into the concept of a primitive root. So a primitive root is a number which, when raised to powers, it ends up covering all of the remainders other than 0. So 3 is the primitive root of 7. So 3 to the 1 is 3, 3 to the 2 is 9, which is 2. So as you can see, it fills all the wheels. So you have 1 is 3 to the 6, 6 is 3 to the 3. It will always have a corresponding power. And this helps us because when you raise 3 to any power, we know we're going to get one of these, but we don't know which. So this is the formal definition. Obviously, only if P is prime. So to simplify things a bit, because you can't go into everything. If P is prime, R is a primitive root of P, if and only if for every A from 1 up to n minus 1, there exists K such that R to the K is A mod P. So raising R to any power is equally likely to give you any number ranging from 1 to n minus 1. So, okay, you have 3 to the 3 mod 7. What is the answer? So how do you find the answer? You calculate 3 to the 3, reduce it mod 7, easy. And you have 6. But other way around, it's a bit more difficult. So you have 1. How do you know what 3 to something mod 7 is 1? There are methods to do this, but it basically results to trial and error. And you get that 3 to the 6 is mod 7. So going the other way here is called the discrete logarithm problem. Finding R to the x mod p given R, x, and p is relatively easy, especially since we have algorithms for that. We have the repeated squaring methods and more complex ones, which work to easily get the answer. But in reverse, this problem becomes much more difficult for certain values of p So this is how it's more difficult. So if P is a very, very large prime and P minus 1 has at least one large prime factor, then this problem is considered intractable. So in computing, that's a term for possible, but so difficult you wouldn't do it. So this makes r to the x mod p a one-way function. So this is to help understand what a one-way function is. It's easy anecdote. You can easily make smoothies by putting fruit in a blender, but you can't get the fruit back from the smoothies, right? So if you try to do that, it's basically impossible. So this is how it works. It's easy to go one way, computationally infeasible to go the other one, from a message to an encrypted message. So these two geniuses use this fact to their advantage. They have an algorithm to. It's basically an algorithm that is used to decide on a cipher, right? So you can easily pass notes to someone in class if you both have a secret code, but you have to decide on the secret code in a public place, basically. So there's an easy way to crack that. You just listen in. But this makes it so that you can come up with a cipher in a public space and no one else will know it. So this is an example. Obviously, not large primes, but bear with me. So you agree on two numbers, one of them prime, 73, and one of them is a primitive root. And Alice and Bob both pick two random numbers that are less than p minus 1. So they find the least value. So they basically calculate one end they go through the one-way function. So they calculate 5 to the 8 mod 73. And these are public things. Everyone knows them. Then what they do is Alice takes Bob's output, raises it to her secret power, and Bob takes Alice's output and raises it to his. So these are both public knowledge. So Alice can take y and raise it to the x. And Bob can take x and raise it to the y. So what they get is the same answer. And this is because r to the x to the y is the same as r to the y to the x mod p. So now they have the secret key. But is it really secret? Because we have what r to the x is and we have what r to the y is. Can't we just find then what r to the x to the y is from that? The answer is not really, because it's the same as trying to solve the discrete log problem. This is called the Diffie-Hellman problem. So if you choose p correctly, such that the discrete log problem is impossible to crack, then you basically made it impossible to find out what the secret encryption value is. So this isn't perfect. There are ways to make it more efficient. So especially compared to the elliptic curve Diffie-Hellman, which uses a different piece of math. It's very interesting. You can't get into everything. But its biggest weakness is the lack of authentication. So you have no guarantee that the person that you are communicating with is indeed your target, right? So there might just be someone in the middle pretending to be Bob to Alice that sends her a completely valid key, but it's not Bob's key, it's his own key. So for that, we require an upgrade from the typical one-way function, which is a trapdoor one-way function. So this function goes easily one way and difficult the other way, unless you have the decryption key, D. So this is used cleverly in RSA. It uses a nice trick in number theory, which I really suggest you look into it. But basically, if you choose n to be a product of two large primes, and you choose two integers e and d, such that e times d is 1 mod p minus 1, q minus 1, which are the two primes, then raising anything to the E and then to the D will give you back M mod N. So this is a perfect candidate for our one-way trapdoor function. You have your encryption key E, which is what you're raising M to encrypt it, and you have your decryption key D, which you will raise M to the E to the D to get back N. So, but is this really secure? How do you get, can't someone just figure what D is, right? But doing that is the same as trying to factorize the number N. So if N is very, very large, it's very difficult to find its prime factors. So it takes too much time. So now we have our trapdoor one-way function. So we have, it goes one way, M to the E, and it doesn't really go the other way unless you have D. So you take the cipher message and you raise it to D and you go back. An interesting footnote of this is that you can also decrypt a message using D and then encrypt it back using E. Now, obviously, everyone knows E, so what good does this give you, right? The message isn't secure at all. However, what it does prove is that you're the one that sent the message, because only you know D, so only you can encrypt the message such that if it's decrypted with E, you get the message back. So this is an example. This is setting up. So basically, I just chose P, Q, E, D, such that it all works out. Take my word for it. So what we have here is we have a public key, which is shared. It's put into a public database that is trusted. And you have a private key, which is your own, and you don't let anyone know it, basically, because it's what you're using to decrypt messages. So this can be used for authentication. So Alice wants to confirm that it is her. So it's actually Alice. So she encrypts a message. So she wants to send 20 using her private key D by calculating C equals M to the D mod N, right? So yes. So she raises 20 to 47, which is her secret key. She sends it to Bob, and then Bob can simply raise it to her public key E and get 20 back. So he knows that whoever sent that 20, it was Alice. When it comes to encryption, if Bob wants to send a message, he only wants Alice to read it. So he can use her public encryption key to send his message 22, right? So he sends her what the answer is. Now, this is public, anyone can see it, but only Alice can decrypt it and get 22 back. Because only she has the D, such that M to the E to the D is actually M. So these two steps can be combined for a very efficient communication. So Alice wants to send a message to Bob, and she wants Alice to know it's her, and she wants Bob to, only Bob to read it, right? So it's a secret. So she encrypts it using her private key, so Bob knows it's her. Then she encrypts it using Bob's public key, so only Bob can read the message. So Bob would take that, decrypt the message using his private key, and then Alice's public key. So he knows that, one, only he can read it, and two, that it's actually Alice. So this isn't perfect, right? If your decryption key is found, all of the message you've sent using the key are compromised. So you've talked to 500 people, and now anyone who is listening in, keeping the data, is now, he knows all your secrets. So this can be remedied using a combination. So if you first use RSA and then use Diffie-Hellman, then you both know that it's you, it's actually you, so you don't have this authentication issue. But then you don't have the problem of it being easily cracked. because if someone does crack your key, then there's this extra barrier of Diffie-Hellman. Also, theoretically, there is no proof that integer factorization is computationally difficult, right? So we don't know that for sure. There could be some genius out there that comes up with this method that does it all really quickly and we're all screwed. And there isn't a proof either that RSA is the same. So all we know is RSA is at least as hard as integer factorization, and through experience, sort of no one's found it yet. So now this is a bit of a footnote, right? Because I don't know if I'm over time yet. When I was doing it on my own, I went over time. Anyway, this is basically how elliptic curve cryptography works. It's very interesting. It uses a special type of curve to find it, and it's interactable in a different way. But yeah, it's an interesting read. I did suggest it. So that's all really. So if anyone has any questions, go ahead.
In the beginning, there was this question about how can you flip a coin through telephone. So this made me think about the notion of randomness. So it's certain websites, for example, allow you to generate random passwords to use for one time. For example, Google Authenticator. But computers can't really truly generate randomness, because they would either rely on external factors or on an algorithm. Is it like, for example, when let's say you have a set of algorithms in order to generate a certain password at a certain time, which changes with time. So if a person cracks that particular algorithm in order, for example, to encrypt certain data, how is it like considered randomness? Because it's like a systematic way.
Well, the method I was thinking of, the answer to that question is it depends on humans themselves being random, which is also flawed. But what you're talking about is pseudo-random numbers, which it will always not actually be random, but there can be algorithms that sort of simulate that. What you're bringing up is interesting, because there's a
like even
there's a
probability,
case,
like the throwing of the coin. It's not like it's not purely random. If you consider all cases, it's all dependent on infinite amount of cases. For example, even the atmosphere you're throwing the coin in, or the way you throw the coin. For example, I can increase my chances by knowing how much distance I'm throwing it in order to get like. That's why there's the issue of connecting likelihood with the amount of times an occurrence can occur. And it's a very weird notion also to connect them, like logically. How can likelihood is connected to occurrence? Even if you consider all of the infinite amount of factors that cause that certain outcome.
Well, that's a philosophical question, though.
I was going to say it's a bit philosophical. I wanted to say, though, also I wanted to add something, because I think Adriana put that in her slide, the bit about coins over the phone, like the emphasis being on the over the phone bit, like not the coin bit per se. Like if you flip a coin and you like heads means you win, like how could, like, you're just going to tell the guy heads no matter the outcome? Like how would you trust the guy? And that's what Adriana was focusing on, if I understood. That's why you put
exactly.
it there.
Yeah, but what I wanted to connect is encryption with randomness. Do you think that we
Do you
would
guys
reach-
mind if I butt in here? I don't know if it's super windy, but the really important thing here is that the pseudo randomness you're mentioning, Arsenius, puts the onus on all the people involved. So even if you say you take a pulsating star, for example, and you count the pulsations, for example, and you generate a very long random number using that, or pseudo random number, the onus is on both people. So the difficulty is on both people. So for true randomness, there are natural processes which are truly random enough. If you look at a hydrogen atom, for example, and you take the electron in the hydrogen atom, it will emit some light completely randomly. This is wave function collapse in physics, and this is why quantum computers are a source for true randomness. But as Luke is saying, I don't think it's that related to Adriana's presentation, which, by the way, I'd really like to compliment you both on your slides and your presentation and the delivery, Adriana. I really enjoyed it, so thank you.
Thanks.
Does anyone else have any questions for Adriana? Okay, I have one maybe. Like, so you mentioned the elliptic curves at the end. Like, could you like mention maybe a bit like why and what makes them sort of special? Like, is there, you know, what makes, why those curves? Like a weirdly specific thing, no? Like a weirdly specific equation, like what y squared equals ax cubed plus bx plus c, something like that.
So, to be honest, it was a lot of stuff. Okay. It's just a rabbit hole that keeps giving you things. We look into it. And I think the point is that what makes them special, if you get 2 points on a line, you'll get a tangent that will only intersect at 1 point. So,
yes, that's
so
basic.
that's the basis of it. Then modular arithmetic is involved as well, because you do that mod something, and it looks like
like a big box of random dots, so basically.
It's cool stuff.
That's very nice stuff. Okay, then. So I guess, you know, that lingering silence suggests that there aren't any further questions. I'd like to, you know, join Jake in complimenting your presentation, delivery, and slides and everything. It was very nice. Particularly like the blender thing and the string going around the clock. I never thought of it that way. Okay, so next up we have Ethan, and he's going to do basically the same thing. He's going to talk about mathematics in some sort of physics sense. Take it away. Oh, hang on, wait. Is there something in the chat? Oh, no. Okay, Alex just added a comment about the integer factorization thing. I think Adriana mentioned this. No, Alex, like we don't know how hard it is, the integer factorization thing. Is that? Okay, thanks for that. So, Ethan, fidejk issa.
Fidejja. Xerja. Nittaraw?
Yeah.
Awesome. Mela. So today I'm going to talk to you guys about geometry in physics. I'm going to start off by just kind of describing what geometry is, although I think most of you kind of know that. I'll describe a little bit between the differences between Euclidean and non-Euclidean. I'll talk a little bit about theoretical physics, and I'll see how what geometry has to do with different areas of physics. So we'll have different examples in classical mechanics, quantum mechanics, and gravitation. So what is geometry? So Oxford Languages describes it as the branch of mathematics concerned with properties and relations of points, lines, surfaces, solids, and higher dimensional analogues. Again, I mean, it's something we do in O-level, right? We figure out areas of shapes and you know, volumes of it and stuff like that. So that's mostly the realm of Euclidean geometry, where, well, then there's also the other side, which is non-Euclidean. So it's kind of yin and yang almost. So what's the difference, right? So Euclidean geometry basically, it's based on Euclid's axioms, one of which is that angles, so if you have two lines intersecting a third, the interior angle, the sum of the interior angles will be 180. Well, this will basically say that these lines will never meet. But in non-Euclidean geometry, this may not be the case. This does lead to two other possibilities, right? So if they never meet, then either they diverge or they converge. So in fact, there are three different types of geometry that come out of this. So you have hyperbolic geometry, where lines of this type, so when you have the interior angles summing to 180 degrees, they will diverge away from each other. Euclidean geometry, which, as I said before, they will remain parallel, and elliptical geometry when they will converge. And some may think I'm crazy here, saying, "Oh, why would this? When would such a thing work?" And well, we don't live on a flat Earth, and this is actually very true on the surface of a sphere. So if you consider, for an example, you see these two lines of longitude here. They have a 90-degree angle with the equator, and you can see that they converge both at the North Pole and if you continue the lines to the South Pole. One thing to notice, however, is that this kind of changes our perception of distance. So now we would like to measure distance along the sphere, because that's kind of the true distance of what's happening. So you see, locally, we can think of a Euclidean space. We would measure distance using Pythagoras' theorem. And as you can see here, you'd get the 90-degree angle, and you find the length of this side using the length of the other two sides. But of course, since because of this property that the interior angles sum to 180 does not imply that they're parallel, you end up with a triangle like this one here, where you have the sum of interior angles greater than 180 degrees. So this exactly isn't possible. So we're going to have to amend our notion of distance a little bit differently. So let's consider 2 points in R cubed. So let's talk about Euclidean geometry, and kind of I'll make a little bit of a generalization from Euclidean geometry. So Euclidean geometry tells us the distance between 2 points, as I said before, is the Pythagorean distance. So that's just Pythagoras' theorem in 3 dimensions. So we can rewrite this as the norm, or the length, the magnitude of the distance between the two vectors. So where we just subtract the coordinates from one another. Another way of writing this norm is just by square rooting the dot product. And if we square both sides, we end up with just the cube of the the square of the components, the sum of them, which can be rewritten in a matrix notation like this. So you have the transpose of R multiplied by R itself. But identically, you can put an identity matrix in between there, and it will remain exactly the same. The notions of non-Euclidean geometry, or rather differential geometry, which tries to explain non-Euclidean geometry, basically says, what if this matrix here was not an identity matrix? Well, that matrix has a name. We'll call it the metric tensor. I won't go into what tensors are, but it's just a name for now. It's just a measure of the curvature of the space in some general sense. It's usually a matrix. So if we're talking about 3 dimensions, it will be a 3-dimensional matrix, and you can continue for higher dimensions. But it is, excuse me, it's symmetric but not diagonal anyways. So we can then basically rearrange our formula for distance by just going back to this thing here. So this is our R3, which is our and our R2 anyways. Our R3 and R3 transpose and R3, and this would be our G. So that gives us exactly this equation like that. So an example of this, looking back at spherical geometry, would be, well, this would be the metric in spherical geometry, where r is the radius of the sphere and theta is the line of latitude, I believe. So at the end of the day, this is a talk about physics, right? So what exactly is theoretical physics? Well, you know, the nice quote from Wikipedia tells us that it's the branch of physics that employs mathematical models and abstractions of physical objects and systems to rationalize, explain, and predict natural phenomena. So yeah, basically, we want to write equations that describe the universe, right? So we've got a couple of different ideas of how we would do this. How would we do this mathematically? So one thing that we like to describe is like to describe the dynamics of a system or a physical object based on its interaction with the environment. And naturally, when you want to describe an environment, you have to describe the geometry of that environment, right? And there are a couple of different tools that we use to describe this geometry. One thing, so some of them, well, two main ones that we use are potential energy and the stress energy tensor. So I'll come back to the stress energy tensor a bit later, but for now, potential energy, it's the energy stored in a body or a system as a consequence of its position, shape, or state. So it is the ability to do work. So if, for an example, I hold this pen here at a certain height, it will want to, in the current gravitational field that I exist in, it wants to fall down. So when I hold it up, it has the potential to have a certain amount of energy just before it hits my table here. So mathematically speaking, it's a scalar field. So it's basically a function that maps every point in space onto a real number. And that brings us on to some examples. So classical mechanics, I'm sure many people are familiar with. It's basically the mechanics of how things move. And we would like to, so given a particular setup, how would we describe the motion of the physical objects? So if we say, for an example, as I said before, a particle here, what path in space will it take? What path will it take if I let go of it, you know? Or another example, another one, which is if I have a ramp, how does that ramp change what the path of the physics? And so what that does basically is we can use a potential to describe the different, the basic geometry of the area we're looking in. So classical mechanics does assume that we're working in Euclidean space, unless we're not, but in most cases we do think of Euclidean space. And all, you know, classical mechanics just comes down to determining the potential and kinetic energy of the system. Now, the kinetic energy typically is just a product of the coordinate system that you choose. So if we're talking Cartesian coordinates, it's just going to be half mv squared, basically. So Lagrangian mechanics, there's also Hamiltonian mechanics and Newtonian mechanics. And Newtonian mechanics is what everyone's familiar with, so I'm going to deal with the unfamiliar here. Basically, we take the difference between these two. So we determine the potential energy based on the geometry, and we throw basically what we get from this equation by defining the Lagrangian into the Euler-Lagrange equations to determine the equation of motion. The equation of motion is a set of differential equations that basically, when solved, you can get the path that the object takes or the system takes in space. So that's the Euler-Lagrange equation. So basically, we just throw whatever we get in here. We take the derivative with respect to velocity and take the time derivative and set that equal to the derivative with respect to space. So basically, yes, the path taken ultimately depends on the potential energy, since the kinetic energy will always be some variant of half mv squared. So we can move on to quantum mechanics a little bit, give another example here. So quantum mechanics deals with wave functions, right? So what are wave functions? A wave function basically, it's a quantity that's related to the probability of finding a particle at a given position at a given time. So typically the time evolution of a wave function is well defined for most basic situations. So we generally solve something called the time-independent Schrödinger equation to determine how this wave function looks like. But at the end of the day, the only thing that changes from time to time. So when we solve this equation, we'd like to solve for our wave function and for our energy values. So if you think of this as a linear system, this is just an eigenvalue problem. You would like to find the energy eigenvalues of the system anyways. But all of this depends on the potential of the system. So the potential energy V in this case, which, you get different solutions for different values of V. So here are a couple of examples. So the typical example, the first one would be the infinite square well, which basically have a potential well. So I've got some diagrams in the next few slides. But you basically have a particle in a box in some sense. And the second one is a particle in free space, but there's a barrier of some sort. So let's have a look at these. So the infinite square well, basically, here we say, so the potential is infinite on the edges, so a particle cannot exist beyond the edges, but is 0 here, so it can exist anywhere in between here. And a possible solution here would just be the standing wave solutions. So you just have something like that, where it's 0 on either end. One thing to note is that the probability of finding a particle is the square modulus. So the probability is always positive. So it's above here. So you have a chance that kind of looks like that. You're more probable to find it here and here than here, for an example. So another different geometry based on the potential is the barrier. So here, this is an effect called quantum tunneling, right? So if you have a potential barrier, given some finite potential here, it's free to move anywhere. So you have a sinusoidal sort of solution anywhere else. It has a decaying chance of finding the particle inside the potential. And as you can see, the amplitude decreases on the other side. So if you were to square these waves and find the probabilities, you'd see that, oh, there's a very regular probability of finding it anywhere on this side. However, there is a small chance of finding it on the other side of the barrier. So in that sense, quantum mechanics tells us that these particles can somehow go through walls in that sort of sense. So finally, I'll move on to gravitation. So gravity, Einstein basically, without non-Euclidean geometry and differential geometry, none of his gravitational theory would be a thing, because it's completely based on the idea that mass and mass influences the shape of the gravity. So this is described. So basically, the idea is that we describe space-time, right? And how space-time, so now we're talking about a 4-dimensional space rather than 3. So we have the regular 3 that we look at plus the time dimension. Though typically we only draw 2 on diagrams because two-dimensional flat sheets, right? So yeah, we describe the geometry of our space-time using this equation. So this equation is a very It's a tensor equation. So again, I'm not going to go into what that is, but basically the idea is that on the left-hand side here, we have all of our terms that have to do with the geometry. So as you can see, there's this G from before. This is the metric tensor. And these are other things that have to do with curvature. And on the right-hand side, we have this stress energy momentum tensor multiplied by some physical constants. So the whole idea basically is that whatever happens here, so this is a set of differential equations, right? And we'd like to solve. So if we know the mass distribution, we'd like to figure out what the geometry looks like in that sense. So, and conversely, if we know the geometry, we can find the mass distribution with these sets of differential equations. I mentioned this before. This is the stress energy tensor, which basically, since we know E equals mc squared, so that's the energy density, right? It's a measure of how much mass or how much energy and quantities that have to do with it. So like, for example, the momentum of that energy and the pressure in between the particles. It's a measure of the amount of mass in a given area. So now we've got a 4D spacetime, so we've got a four-dimensional matrix, but that's the gist of it. And this all sums up very nicely in a quote by Wheeler. Space-time tells matter how to move, but matter tells space-time how to curve, and which is exactly the case. So if you have matter, if you know your matter distribution, you can find your geometry. And in turn, once you know the geometry, you can figure out all of the kinematics of how things move in that space-time. And if matter tells space-time how to curve, so space-time it's a big interplay between the two different things. So thank you for listening. That was my talk. Do you have any questions?
Thanks a lot, Ethan. I have one question, if I may start. Like, I don't know if it's a silly question or something. Like you said that when you had the barrier, there's like lots of waves here and like tiny waves here. So there's like a large probability that's here when you square it, and the small probability. How does one interpret like that little decay bit?
So that's if I recall correctly.
If the particle is like in the wall, basically, there's a probability that will be there.
Yes, but it's quite small, I believe. Well, it's all pretty much negligible because it would be like some e to the minus 2 compared to the sine waves. So
hang on. So in the drawing, because in the drawing it was like high, sort of going down, and then
yes,
the lowest.
I can share the drawing again if you'd like to see it.
But what's the physical interpretation of that little slopey bit? I guess that's what my question is.
So the physical interpretation here. So here, this is just the wave function. The probability is the modulus squared of this function. So it would you'd have like the curves like that, and this would you just square that. So that would be an even smaller probability. So yes, there would basically be a very small chance, but it's negligible compared to what's on the other side, and what's outside the wall.
Okay.
I if I can like butt in, I wouldn't say it's negligible. I think so. Tunneling is so there are sensors like pressure sensors. There are even cases where very complicated watches that need to be used near like places near the Arctic Circle where people can't use their hands, or on the moon. Their touch screens will make use of tunneling. So the pressure that your finger can put on the glass will affect the amount of tunneling that the particles in the glass are doing, and we can sense that. So I wouldn't say it's negligible, but it is smaller than I'm just sort of adding
that's a fair point. Yes.
So the term tunneling itself refers to this little to that effect basically of the going through.
Yeah, the idea of going through the wall basically.
Okay.
Yeah.
I wanted to ask a question about this instance, Ethan, and this isn't a trick question, Jafir. I'm curious to see your take. Where would you say the geometry is in this situation? Are you interpreting it as it is in the potential? Where am I coming from? I'm coming from a place where
my idea basically is that the geometry determines the potential in some sense. So if you have a barrier there is a certain amount of potential that you need to require to overcome that barrier, a physical barrier, I mean, in some sense. Whether it's an actual wall or like an electromagnetic field, that's not of the matter at the moment. But this is more of a horistical view, if you know what I mean.
Sure, cool. What I'm trying to maybe allude to is that quantum mechanics is a very information-heavy thing, right? So a lot of times it almost does not care about your geometry. So jinta l-opinjoni, per eżempju, li jekk tbiddel potential, ma jfissirx neċessarjament qed tbiddel geometry inti. So like your inner product is still working the same way. A place where this would change is somewhere where so in quantum field theory, there's something called the Klein-Gordon equation, for example. And the way that a quantum field is going to move through space is going to be affected by the curvature of that space and so on. But this is very, very specific. So I would say that is an example there. And I just wanted to flag this a bit. I want to also note, like, Swetchy, thank you for taking the time to prepare this. It was really fun to hear someone else blabber about physics in the MMS barrayin. So hopefully kuna miktar minna min dejqu l-maths people bil-physics.
Have to indoctrinate more people.
I agree. Alex commented in the chat. He said, "Thank you for explaining things clearly for someone who wasn't very physics savvy." Basically, I mirror that sentiment as well. It's a very interesting talk. Sabiħ il-Bahar Jake.
All right, al-Munshar, all
right. Does anyone else have any questions for Ethan?
I actually just joined, so I didn't listen to the whole conversation. But I must remark that I don't agree with Jake, because I think studying correlation functions is one of the new subjects to actually study how the geometry is restricted, especially in holographic theories. So it's not true that.
Għandek f'moħħok għandek enough something like convex sets and stuff like this for density matrices. Is this what you have in mind?
In holography, what is really strong basically right now is that entanglement entropy, which I don't know, I guess you know what it is, actually restricts the geometry of the bulk theory. So it's something which is really strong right now. And what is going on right now is trying to generalize this to just correlation functions and to study how these restricted the geometry. So what you said is that I think if I understood right, you said that quantum mechanics doesn't affect the geometry. Is that what you said, Jake?
No, I said that it's a very in my opinion, l-etnejtin jissapporta l-ettejtin. So let me maybe refine what I said. Oh, by the way, etneħu Bazli għawinti hello, li jena għettu li quantum mechanics is inherently an information theory subject, and it starts to affect geometry, precisamente fi ettejtin, when it starts to come to these large quantum mechanical structures where you have quantum field theory work. And I agree that it's remarkable that we have theories like ADS-CFT, kif ettejtin work, illi you're starting to see a statement about information affecting a geometry, like an actual geometry. It's remarkable. I totally agree.
Yeah, that kollox la għolib minna.
Xaħt għandu ktar domandi? Morna full circle, ġifiri jek Ethan was right all along.
Like maybe to refine this point a bit, right? Ethan was talking about a potential in something like ADS-CFT, and even Jean-Pierre, if you want to jump in here. You have something like that, but quantum state. So also imagine għandek ma nafx marriċ ġifiri għal min forsi mhuwiex daqshekk mitħla marriċ nħu ħafna ħin. Imma an arbitrary quantum state, so to speak, contains some amount of information about how sort of these quantum states are distributed. And what ADS-CFT does is it relates these quantum states to states to statements not about the information, but about in for example the case of ADS-CFT, a space-time, right? The way a space-time is curved, and they make this a very, very direct relationship. So jaqbdu ċertu per esempio thermal states, and when you look at the thermal state from an information sense in the quantum field theory, it looks like this quantum state. And you can find a gravity dual for that, which would be like a geometric statement about the space-time. And there's an equivalence there. I don't know if John wants to add.
No, that's basically it. Actually, if someone is really interested in going into this stuff, the ADS-CFT hasn't been mathematically proven. It's just a conjecture, right? So if someone wants to go into this from the mathematical point of view, is really interesting and really cool.
Jena naqbel ma' Zanina bħala speċi, this was like a tasting session, I suppose, għalina, speċi biex nara daw kif. It's interesting. I sort of loosely knew this, you know, that like you need to sort out this whole problem with the, you know, a triangle on an orange skin or whatever. I've never actually seen how one inserts that G matrix in the middle and so on. Not my that Sabiha.
Thank you.
Thanks again to Ethan and to Adriana for their very interesting talks. Proset, you know, they're both very, very gripping. I really enjoyed listening to both of them. So, have a nice day, everyone. Then.
Cheers.
Ciao, ciao. Thanks everyone for attending.